The morning of April 17, 1944, at Dravo Corporation's Neville Island shipyard, a welding supervisor named Carl Rasmussen stood watching something that shouldn't have been possible. Behind him, LST 729 sat in the final assembly position, barely 70 hours old from keel laying to nearly complete hull. Ahead of him, 3 more LSTs occupied progressive construction berths, each at a different stage of completion, all moving forward like products on an automotive assembly line. Except these weren't cars. These were ocean-going warships, each longer than a football field, and they were emerging from Pittsburgh steel at a pace that made traditional shipbuilders think Dravo had discovered black magic. Rasmussen checked his clipboard. The Navy had just issued the impossible order. Operation Overlord, the invasion of Normandy, needed every LST America could produce, and they needed them 6 weeks ago. Dravo's normal production rate, 1 ship every 6 days, wasn't enough. The order came down from Washington through Admiral Robinson himself. 15 LSTs in 45 days, 1 ship every 3 days, the hot ship program they were calling it, and Rasmussen knew exactly what it meant. His welders would work overlapping shifts, materials would flow without pause, and every innovation Dravo had pioneered over 3 years of LST production would be pushed to its absolute limit. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The gamble was staggering. LSTs were already the most desperately needed vessel in the entire Allied arsenal. Without them, Eisenhower couldn't land tanks on French beaches. Without them, MacArthur couldn't island hop across the Pacific. Winston Churchill himself had written that the destinies of 2 great empires seemed tied up in these goddamned things called LSTs. And now Dravo was promising to build them faster than anyone thought steel and human hands could manage, using production methods that turned traditional naval architecture into something that looked more like Henry Ford's assembly line than a shipyard. But Rasmussen wasn't worried. He'd watched Dravo transform shipbuilding once already. He'd seen welding replace riveting, prefabrication replace piece-by-piece construction, and assembly lines replace craftsman tradition. The hot ship program wasn't reinventing their process. It was simply proving what they'd known all along. When you combined the right engineering innovations with the right production philosophy, industrial capacity became a weapon more decisive than any gun. The story of how Dravo got to this moment, how a Pittsburgh company that built barges and bridge components became the lead designer and manufacturer of the war's most crucial amphibious vessel, started 3 years earlier with a phone call that would reshape American naval power. January 1942, 6 weeks after Pearl Harbor threw America into total war, Admiral Samuel Murray Robinson, chief of the Bureau of Ships, summoned 2 men to Washington who'd never built a warship in their lives. James D. Berg, chairman of Dravo Corporation, and Vincent B. Edwards, the company president, arrived at the Navy Department knowing only that the meeting was urgent and classified. What Robinson showed them was a preliminary sketch of something the British were calling an Atlantic tank landing craft, a vessel that could carry 20 Sherman tanks across an ocean, drive itself onto an enemy beach, open massive bow doors, drop a ramp, and discharge its entire cargo directly onto hostile sand. The British had tried building prototypes. 3 converted tankers from Lake Maracaibo, shallow draft vessels with retrofitted bow doors. They'd worked adequately in the Operation Torch landings in North Africa, but they were stopgap measures, conversions of existing ships. What the Allies needed was a purpose-built design, manufactured at scale, produced in numbers that would make amphibious invasion not just possible but inevitable. The British couldn't build them. Their shipyards were overwhelmed, their industrial capacity stretched beyond breaking. They needed American production, American steel, American assembly line thinking. Robinson laid out the numbers that made Berg and Edwards understand the scope of what was being asked. The Navy wanted 1,000 LSTs. Not eventually, not when convenient. They wanted production to start immediately, with the first vessel delivered within months. Each LST would be 328 feet long, 50 feet wide, capable of carrying 700 tons of cargo and equipment. They'd need to cross oceans, survive torpedo attacks, withstand rough seas, then deliberately beach themselves on hostile shores while under fire. Traditional shipbuilding methods took 6 to 8 months per vessel. Robinson needed them in weeks. Berg and Edwards didn't hesitate. Dravo accepted the contract as lead yard within 48 hours, committing to a $195 million shipbuilding program and a $24 million plant expansion. But they weren't accepting because of patriotic duty alone, though that mattered. They were accepting because they'd already solved the central problem Robinson thought was impossible. They'd figured out how to mass-produce ships a decade earlier, and nobody in the Navy knew about it. 1929. The Depression had devastated American industry, but it also created opportunities for companies willing to innovate. Dravo was building river barges for its own operations, standard hopper barges 175 feet long. Traditional shipbuilding meant riveting, hundreds of workers with hammering guns, beating red-hot rivets into overlapping steel plates. It was slow, labor-intensive, and required skilled craftsmen. The welding equipment manufacturers claimed they had machines and electrode wire that could join thick carbon steel plates faster and stronger than rivets. The shipbuilding industry, locked in economic doldrums, neither believed them nor tested the claim. Dravo decided to try. They built an experimental barge, number 817, using electric arc welding instead of rivets. Every seam welded, no hammers, no riveting gangs, no overlapping plates. The barge worked. More importantly, it worked better than riveted barges, and it was built faster with fewer skilled workers. By 1935, Dravo had developed a complete production line for welded barges, building 3 standard hopper barges simultaneously in a massive fabrication shop that guaranteed 24-hour assembly, regardless of weather. The real innovation wasn't just welding. It was how Dravo approached construction. They broke barges into shop-built pre-assemblies, large sections fabricated under controlled conditions with precise welding techniques, then transported to the final assembly area. A standard barge became a collection of modular components that could be built in parallel, stored until needed, then assembled rapidly. The production time collapsed, the quality improved, the cost dropped. But they still had one problem: moving completed or partially completed hulls around a shipyard. Traditional yards used sloped ways, floating ships up inclines into dry docks. Dravo's engineer came up with something different: a transfer buggy, a 4-wheeled carriage running on tracks with built-in hydraulic jacks capable of lifting 300 tons. Multiple buggies could lift an entire hull clear of its construction berth, roll it forward to the next station, and lower it precisely into position. The hull moved through progressive construction stages like an automobile moving down an assembly line. These 3 innovations, electric arc welding, shop-built pre-assemblies, and movable hull construction, formed the backbone of Dravo's production philosophy. By 1941, when the Navy came looking for someone who could mass-produce warships, Dravo had been refining these techniques for over a decade. They'd built the infrastructure, trained the workforce, and proven the concept. All they needed was the right product to demonstrate that assembly line shipbuilding could work at scale. The LST was that product. When Admiral Robinson's team reviewed Dravo's facilities at Neville Island in 1940, examining the barge production lines and welding operations, they saw what traditional naval architects had missed. This wasn't a barge company pretending to be a shipyard. This was an industrial engineering operation that treated ships as manufactured products. The Navy awarded Dravo the first contract for submarine chasers, patrol craft 165 feet long. PC-490 launched on October 18, 1941, making history as the first combat Navy vessel ever built on an assembly line, the first sea-going warship launched from an inland river shipyard. The Navy watched carefully. If Dravo could build patrol craft using assembly line methods, could they scale to something larger? The LST design that arrived from the Navy's Bureau of Ships in early 1942 answered that question. The preliminary drawings came from John Niedermair, technical director of preliminary ship design, who'd sketched the concept in November 1941 after meetings with British Admiralty representatives. His challenge was resolving contradictory requirements. The LST needed deep draft for ocean crossings, but shallow draft for beaching. It needed to be large enough to carry substantial cargo, but light enough to retract from beaches. Niedermair solved it with a massive ballast system and an unusually wide beam relative to length. Traditional destroyers had a 10-to-1 length-to-beam ratio. The LST was 6-to-1, distributing weight over a broader area. Ballasted. For ocean transit, the LST drew 14 feet aft. With ballast pumped out for beach operations, the forward draft dropped below 4 feet. The ship could literally drive itself onto sand, discharge cargo, then winch itself backward using stern anchors. The bow doors and ramp design came from British concepts, massive clamshell doors that opened to reveal a ramp connecting the tank deck directly to the beach. The design was revolutionary for amphibious operations, but a nightmare for traditional construction. The LST contained roughly 8,000 individual components, required precise welding throughout, and needed to be both ocean-going and beachable. Navy Ordnance officers estimated 6 months construction time using conventional methods. Dravo looked at the same blueprints and saw an opportunity to prove their assembly line philosophy at unprecedented scale. The contract arrived in January 1942. Groundbreaking at Dravo's Neville Island facility began 27 days later, without fanfare, without ceremony. The existing West Yard expanded dramatically. A half-mile away, Dravo purchased a 66-acre field and designated it the East Yard. The Navy Department built 5 miles of modern 4-lane highway and an auxiliary 2-lane timber bridge across the Ohio River's back channel just to move workers to and from the yards. Within 90 days, Dravo had transformed from a barge manufacturer employing 1,500 workers into a major naval shipyard. The workforce explosion created training challenges nobody had anticipated. How do you teach someone who'd never seen a ship to weld hull plates that had to withstand torpedo explosions? Traditional apprenticeships lasted years. Dravo needed welders in weeks. They borrowed the same philosophy that made assembly lines work: break complex skills into simple, repeatable tasks. Don't train master welders. Train specialists who could perform one specific operation perfectly. Women flooded into the welding courses that began in fall 1942. The Pittsburgh Press described them begging to get into classes at South Vocational High School. The Women's Bureau of the Labor Department issued warnings that welding was unsuitable for women, that shipyards would be too physically demanding. The women showed up anyway. Bessie McCarroll from McKee's Rocks. The Jurjevic sisters, Vera, Julie, and Anne, 3 of 6 daughters in a Croatian immigrant family from North Perry. They learned to weld in weeks, then joined crews building LSTs alongside male welders. By summer 1942, the prefabrication system was operational. Massive covered sheds housed welding stations where hull sections no larger than 30 feet in any dimension were constructed from detailed sequence cards. Unlike traditional welding that started at edges and worked inward, locking residual stress into the metal, Dravo's engineers had studied stress distribution. Their welders started at the geometric center of each section and worked outward in spiral or radial patterns, allowing stress to dissipate toward the edges rather than concentrate at critical points. This wasn't academic theory. This was practical engineering learned from building thousands of welded barges. Steel expands when heated, contracts when cooled. If you weld continuously from one end to the other, the cooling contraction pulls the metal, creating warping and locked-in tension. But if you weld from the center outward, alternating locations to prevent heat buildup, the stress distributes evenly. The finished sections lay flat and true, ready for assembly without the corrections and adjustments that plagued traditional construction. Each welded section went into stress relief ovens after every 10 welds, heated to 1100 degrees Fahrenheit and slowly cooled. This annealing process allowed the steel's crystalline structure to relax, eliminating residual stresses before they accumulated to dangerous levels. It, added time to prefabrication, but saved enormous amounts of time during final assembly, when stressed sections would have required rework. The steel itself arrived pre-cut and pre-formed from rolling mills that had retooled specifically for LST production. Curved bow sections came shaped to exact specifications. Deck plates had pre-drilled bolt holes for temporary alignment. Frame sections arrived as pre-welded assemblies. Dravo didn't cut and shape steel on site. They assembled components that were ready for immediate installation. September 7th, 1942. 219 days after receiving the contract, LST-1 slid into the Ohio River from Dravo's west yard. A sign stretched across the hull read, "Forward to Victory, America." The launch made front-page news across Pittsburgh. Radio newscaster Lowell Thomas attended with 10,000 spectators and broadcast his astonishment. An ocean-going ship, built for Uncle Sam's Navy, built here at Pittsburgh, and launched here at Pittsburgh. A ship of steel, more than 173 feet long, to be manned by a Navy crew, doing the job of a destroyer. But Thomas missed the most important detail. LST-1 wasn't built like traditional ships. It came off an assembly line, the first of a type that would change how America waged industrial warfare. The question wasn't whether Dravo could build LSTs. They'd proven that with LST-1. The question was whether they could build them fast enough to matter. Because in early 1943, as Allied planners looked toward invading Europe and island hopping across the Pacific, the shortage of LSTs had become the single greatest impediment to victory. Operations were being delayed, invasions postponed, strategic plans rewritten, all because there weren't enough of these ungainly, flat-bottomed vessels to deliver tanks onto hostile beaches. The production race had started, and Dravo's assembly line innovations were about to be tested against the most demanding customer in history. A military that needed the impossible, needed it yesterday, and wouldn't accept excuses about why it couldn't be done. By March 1943, the crisis had become undeniable. General Eisenhower needed 230 LSTs for Operation Overlord, scheduled for May 1st, 1944. Admiral Nimitz needed 90 for Pacific operations. General MacArthur needed at least that many more for his island-hopping campaign. The Allies had just used 90 LSTs to invade Salerno, south of Naples, and those vessels were tied up in Mediterranean operations. On paper, American shipyards had contracts for over 1,000 LSTs. In reality, production was crawling. The problem wasn't desire or effort, it was methodology. Most LST contracts went to coastal shipyards that built ships the traditional way, piece by piece, plate by plate, with riveting gangs standing on scaffolding. Newport News had laid the keel for LST 386 in July 1942. It took them 133 days from keel laying to commissioning. At that pace, filling the Navy's orders would take until 1946, 2 years after the invasions they were designed to support. Dravo's approach was fundamentally different, and by spring 1943, the results were becoming visible. The Neville Island yards had evolved into a choreographed industrial operation that bore no resemblance to traditional shipbuilding. The process began miles away from the shipyard, in fabrication shops where steel arrived pre-cut from Pittsburgh's massive mills. U.S. Steel, located within miles of Neville Island, provided an endless stream of plate steel, rolled to specifications, cut to exact dimensions, ready for welding. The fabrication shops operated 3 shifts, 24 hours, 7 days a week. Each shop specialized in specific LST components. Shop A built hull bottom sections. Shop B fabricated side plates and bulkheads. Shop C handled deck assemblies. Shop D produced the bow section with its complex door mechanisms. The specialization meant workers repeated the same operations endlessly, developing speed and precision that generalists could never match. Inside Shop A, a hull-bottom section began as 23 separate steel plates, ranging from quarter-inch deck plating to 3/4-inch reinforced sections. The plates arrived on rolling carts, positioned on massive steel jigs that held them in precise alignment. Welders worked from numbered sequence cards that specified every weld in order. Weld 1, always the center seam running longitudinally down the section's middle. Welders started at the geometric center of that seam and worked outward in both directions simultaneously, two welders mirroring each other's progress. The welding itself was electric arc, using Lincoln Electric equipment that Dravo had refined over years of barge construction. The electrodes were coated rods that created a protective gas shield as they burned, preventing oxidation in the molten weld pool. The current settings, the electrode angle, the travel speed, all were standardized and taught to each welder until they could perform the operation without conscious thought. A skilled welder on a hull bottom could lay a perfect bead at 18 inches per minute, hour after hour, maintaining consistency that riveted construction could never achieve. After Weld 1 cooled, the sequence card directed welders to Welds 2 and 3, perpendicular seams connecting the longitudinal plates to transverse reinforcements. Again, starting from centers and working outward. The pattern continued, spiraling outward from the section's center, distributing heat and stress evenly across the growing assembly. Every 10th weld, the section moved to stress relief ovens, massive gas-fired furnaces that heated the entire assembly to 1100 degrees and held it there for 2 hours, before slowly cooling over 6 more hours. The stress relief was critical, and it was something traditional shipyards skipped because they couldn't afford the time. But Dravo had learned from barge construction that stressed steel caused problems later. Warping, cracking, failure under load. Better to spend 8 hours stress-relieving a section during fabrication than spend 3 days correcting problems during final assembly. The math was simple. Time invested in quality during prefabrication paid dividends in speed during final construction. A complete hull bottom section, 30 feet long and 25 feet wide, required 47 individual welds and 5 stress relief cycles. From first tack weld to completed section took 63 hours. But here was the magic of prefabrication. While one hull bottom moved through its welding sequence, 20 others were at different stages in parallel. Shop A didn't produce one hull bottom in 63 hours. It produced one hull bottom every 3 hours because multiple sections flowed through the process simultaneously. The same parallel production happened in every fabrication shop. Side plates, bulkheads, deck sections, bow assemblies, engine mounts, fuel tank assemblies, all built simultaneously in dedicated shops, all using the same center-outward welding sequences, all stress-relieved, all held in storage yards until final assembly required them. By summer 1943, Dravo's storage yards contained hundreds of prefabricated LST components, a just-in-time inventory system that fed the assembly line without delay. The final assembly berths were where prefabrication paid off. Traditional shipyards started with a keel and built upward, plate by plate, in a single location. Dravo's transfer buggy system meant hulls moved through progressive construction stations, each station performing specific operations. Berth 1 received the keel assembly, a massive pre-welded structure that formed the ship's backbone. The transfer buggies, running on rails, embedded in concrete, lifted the keel and moved it to Berth 2. At Berth 2, hull bottom sections arrived from Shop A via overhead cranes. The sections, already stress-relieved and dimensionally accurate, dropped into position on the keel like puzzle pieces. Alignment pins and temporary bolts held them, while welders made final connections. Because the sections were prefabricated to tight tolerances, the fit was precise. No hammering, no forcing, no field corrections. The welds connecting sections to keel were specified on the same type of sequence cards, center-outward patterns that maintained stress distribution. Berth 3 received the hull and keel assembly and added side plates. These massive curved sections, pre-formed in Shop B, required overhead cranes and precise positioning. But again, because they were prefabricated to exact specifications, they mated to the hull bottom with minimal adjustment. Welders worked in teams, 4 welders per side, all following identical sequence patterns. maintaining symmetry and balance as the hull took shape. Berth 4 added bulkheads, the internal walls that divided the LST into compartments and provided structural rigidity. 23 major bulkheads, each prefabricated as a complete assembly with reinforcements, hatches and cable passages already installed. They dropped into position and welded to hull sides and bottom in prescribed sequences. Berth 5 installed the deck, the massive flat surface that would carry vehicles and cargo. Deck sections, prefabricated in Shop C, came with reinforcements and tie-down points already welded in place. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Berth 6 was the bow installation, the most complex operation in LST construction. The bow section, fabricated as a complete assembly in Shop D, weighed over 40 tons and contained the mechanisms for the massive clamshell, the doors and the deployment ramp. Hydraulic systems, hinge assemblies, door seals, all were installed and tested in the fabrication shop before the entire bow section travelled to final assembly. Positioning it required synchronized operation of multiple cranes and perfect timing. Once in position, welders connected it to the hull with some of the most critical welds on the ship, joining the bow's structural members to the hull's longitudinal stringers. Berth 7 handled the superstructure, the raised deck area containing the pilot house, crew quarters, and weapon mounts. Again, prefabricated sections, pre-welded and stress-relieved, lowered into position and connected to the main hull. Berth 8 installed engines, transmissions, and drive shafts. The engines, General Motors diesel units built in Detroit, arrived as complete assemblies on their mounting frames. They dropped into the engine room, bolted to reinforced mounts, and connected to pre-installed fuel lines, cooling systems, and electrical harnesses. The final berth, Berth 9, was outfitting. This was where the LST transformed from a welded hull into a functioning warship. Electrical systems, plumbing, ventilation, radios, navigation equipment, lifeboats, davits, ammunition storage, galley equipment, berthing spaces, heads, everything that made the ship operational. Outfitting traditionally took months. Dravo's prefabrication meant most systems arrived as complete assemblies that plugged into pre-installed connection points. Electrical harnesses came pre-wired and labelled, plumbing ran through pre-cut passages, ventilation ducting connected to pre-positioned mounts. The transfer buggy system meant an LST moved from keel laying at berth 1 to launch ready at berth 9 in a continuous flow. No single berth held up the entire line. If berth 4's bulkhead installation ran slow, berth 5 continued deck installation on the previous ship, while berth 3 worked on the next ship's side plates. The line balanced itself, with supervisors shifting workers between berths to eliminate bottlenecks. By fall 1943, Dravo had achieved steady-state production. One LST completed final assembly every 6.1 days. The production rate astounded the Navy, which had estimated 4 to 6 months per ship using traditional methods. Dravo was building LSTs 70% faster than the most optimistic predictions, and they were doing it with a workforce that had never built ships before 1942. The workforce itself was the story within the story. By 1943, Dravo's Neville Island yards employed 16,000 workers. Roughly 40% were women. Roughly 60% had zero manufacturing experience before the war. They were restaurant cooks, maids, farmhands, shop clerks, housewives, recruited through newspaper ads and trained in weeks. The training system was brutal in its efficiency because it abandoned the idea of creating well-rounded shipbuilders. Workers learned one job, practiced until perfect, then performed that job 8 hours per shift for the duration of the war. Anna Kowalski, who'd served coffee at a Detroit diner, learned to weld vertical hull seams connecting side plates to bottom plates. That was her entire skill set. Vertical hull seams on LST hulls. She practiced on scrap metal for 40 hours, then went to the production line and welded vertical hull seams on real ships. 8 hours per shift, 5 days per week. She became so proficient that her reject rate dropped below 1%, better than welders with 10 years of general experience. The assembly line philosophy applied to human beings. Specialization created speed and quality that generalists couldn't match. James Washington, a 58-year-old Alabama sharecropper who'd never operated anything more complex than a mule plow, installed transmission assemblies at Berth 8. The transmission, built by General Motors in Detroit, arrived as a complete unit weighing 1,800 pounds. An overhead crane lowered it into position. Washington's job was guiding it onto 4 mounting studs, installing 12 bolts with specific torque settings, and connecting the output shaft to the propeller drive using a flanged coupling. He'd done it 600 times by summer 1943. He could perform the entire operation in 12 minutes without looking at instruction cards. Margaret Chen, barely 5 feet tall, climbed into turret compartments to wire electrical systems in spaces engineers had assumed only small men could access. The wiring harnesses arrived pre-built with labeled connections. Her job was routing them through pre-cut passages, securing them with clamps every 8 inches, and making connections at terminal blocks using color-coded diagrams. She worked in spaces so confined that claustrophobia was a constant issue, but the pay was 3 times what she'd made at a textile mill, and her 2 brothers were fighting in the Pacific. She considered her cramped working conditions a reasonable contribution to bringing them home. The 3-shift operation meant the yards never stopped. The day shift, 7 a.m. to 3 p.m., was production-focused. The swing shift, 3 p.m. to 11 p.m., was maintenance and quality control. The night shift, 11 p.m. to 7 a.m., was the hardest. Workers called it the zombie shift because human bodies aren't designed to work when every biological instinct screams for sleep. Productivity dropped 15% on night shifts. Injury rates doubled. Workers fell asleep standing up, drifted into moving equipment, made mistakes that day shift had to correct. Dorothy Martinez, working turret assembly on the night shift, fell asleep at 3 a.m., and her hand drifted into a moving conveyor belt. She lost 2 fingers. The factory didn't stop. Her station was filled within 20 minutes by a floater worker trained for exactly this situation. Dorothy was back, on a different station 3 weeks later, because missing fingers didn't disqualify you from war work, only missing hands did. The cold calculus of wartime production meant everybody who could contribute did contribute. The yards became self-contained communities. Dravo built on-site dormitories, housing 3,000 workers who'd relocated from across America, chasing defense jobs. The cafeteria served 15,000 meals per day across all shifts. A barber shop, medical clinic, and post office operated inside the factory complex. Children attended daycare in converted storage buildings, while mothers welded armor plate 200 feet away. The line between civilian life and war production dissolved completely. Workers ate where they worked, slept near where they worked, and their friends were people who worked their station. When the public address system announced Allied victories during lunch breaks, the cheers echoed off steel rafters because everyone understood. Those were their LSTs winning those battles. LST-1, launched from Neville Island on September 7, 1942, participated in the Salerno invasion on September 9, 1943. LST-47 and LST-49, both built at Dravo, appeared in the famous photograph of Omaha Beach on D-Day, their bow doors open, their ramps extended, disgorging tanks and trucks onto French sand. Every ship rolling off the Neville Island ways carried a piece of 16,000 individual stories. Then came April 1944, and the order that would prove whether Dravo's assembly line philosophy could withstand the ultimate test. The Hot Ship Program. 15 LSTs in 45 days, 1 ship every 3.5 days. For D-Day, for Normandy, for the invasion that would determine whether the Allies could re-enter Europe or whether the war would drag on for years. The challenge wasn't just speed, it was maintaining quality at speed. An LST that failed at sea didn't just sink. It took with it 20 Sherman tanks, 40 trucks, 160 men, and a piece of the invasion timetable that couldn't be recovered. Eisenhower's plans assumed every LST would function perfectly under combat conditions. Dravo's reputation, built over 3 years of production, would be proven or destroyed based on whether these hot ships performed when it mattered most. Carl Rasmussen, the welding supervisor who'd watched the first LST take shape in 1942, gathered his team leads on April 20th and laid out the plan. The assembly line would run at maximum capacity, no maintenance shutdowns except for critical repairs. Materials would flow from fabrication shops without buffer stocks. If Shop A fell behind on hull bottoms, production would halt across all berths. There was no slack in the system. Every worker, every shift, every weld had to execute perfectly. The fabrication shops went to overlapping shifts. Instead of 3 8-hour shifts with clear transitions, workers now operated in staggered 10-hour shifts with 4 hours of overlap. During overlap periods, both shifts worked simultaneously, doubling output. The welding bays ran so hot that ventilation systems struggled to clear the fumes. Welders worked 30-minute rotations, 30 minutes on the torch, 10 minutes rest, maintaining quality without the fatigue-induced errors that plagued extended welding sessions. The stress relief ovens, previously running batch cycles with controlled heating and cooling, switched to continuous operation. Sections entered one end, travelled through the heated zone on rolling conveyors, and emerged stress-relieved at the other end. The process time dropped from 8 hours to 4 hours, but the quality remained consistent because the temperature profiles were carefully managed. The transfer buggies, previously moving hulls between berths once per day, now operated every 8 hours. An LST that would have spent 3 days at berth, 4 for a bulkhead installation, now spent 24 hours, with teams working continuously to complete the operation in compressed time. The compressed schedule meant welders worked in tighter spaces with more people, increasing the complexity of coordination. Supervisors walked the berths with clipboards, ensuring weld sequences stayed synchronized, preventing conflicts where one team's work blocked another team's access. The first hot ship, LST 729, moved from keel laying to launch in 84 hours. 72 hours would have been perfect, 3 full days, but an electrical harness arrived from the supplier with mislabeled connections, costing 12 hours of troubleshooting and rework. The second hot ship, LST 730, took 81 hours. The third took 78 hours. By the 10th ship, the system had found its rhythm. 72 to 76 hours per ship, consistent, reliable, faster than anyone believed possible. The quality inspectors crawled through every hull, checking welds with magnetic particle inspection, examining structural connections, testing ballast pumps, verifying electrical systems. The reject rate stayed below 8%, meaning roughly 1 in 12 ships required minor corrections before Navy acceptance. Those corrections happened during outfitting, didn't delay deliveries, and involved issues like misaligned hatch covers or improperly calibrated pumps, not structural failures. On May 27, 1944, Dravo completed the 15th hot ship, LST 743, with 2 days to spare. 15 LSTs in 45 days. The production rate that Navy planners thought was fantasy. And every single one of those ships sailed down the Ohio River, transited the Mississippi to the Gulf, reached coastal fitting-out yards, received final weapons and communications equipment, and deployed to England in time for D-Day. The mathematical reality of what Dravo achieved becomes clear when compared to other shipyards. Newport News, the most established naval shipyard on the East Coast, was building LSTs at an average rate of 130 days from keel to commissioning. Dravo's hot ship program cut that to 3.5 days for construction plus another 2 weeks for coastal fitting out and sea trials. The acceleration wasn't marginal, it was transformational. By June 6, 1944, when the largest amphibious invasion in history began, 173 LSTs participated in the Normandy landings. At least 53 of those LSTs were built in Pittsburgh, either at Dravo or American Bridge Company in Ambridge. The Pennsylvania-built LSTs delivered tanks to Omaha Beach, Utah Beach, Gold Beach, Juneau Beach, and Sword Beach. They beached under fire, opened their bow doors while German artillery ranged in, and discharged Shermans that drove directly into combat. LST-1, the first LST ever built, the ship that launched from Neville Island on September 7, 1942, participated in 4 major amphibious operations: Salerno, Anzio, Normandy, and southern France. The ship earned 4 battle stars, survived countless attacks, and proved that assembly line construction didn't compromise durability. The welds held, the bow doors functioned, the ballast system worked exactly as designed. When LST-1 finally came home in 1945, Navy inspectors found minimal structural degradation despite 3 years of combat operations. The production numbers tell the full story. Between September 1942 and August 1945, Dravo's Neville Island yards built 145 LSTs. The average production time was 1 every 6.1 days, but that average included the learning curve of early ships and the normal pace production between urgent programs. During peak periods like the Hot Ship program, Dravo proved they could sustain 1 LST every 3.5 days indefinitely if the Navy demanded it. Combined with 4 other Midwest yards that Dravo trained in their techniques, the Cornfield shipyards produced 670 of the 1,051 LSTs built during the war. 64% of America's LST fleet came from inland yards that didn't exist before December 1941, built by workers who'd never seen an ocean, using production methods that traditional naval architects insisted were impossible. The telegram arrived at Dravo's corporate offices in Pittsburgh on August 15, 1945. Japan had surrendered. The war was over. Within 72 hours, the Navy cancelled all remaining LST contracts. The yards that had operated 24 hours a day for 3 years went silent. Employment at Neville Island, which had peaked at 16,000 workers in spring 1945, dropped to 1,123 by December. The women welders, the specialized workers, the people who'd transformed from waitresses and farmhands into precision shipbuilders, returned to civilian life without fanfare or recognition. Bessie McCarroll went back to McKee's Rocks and never welded again. The Djurjevic sisters, Vera, Julie, and Anne, found other work in Pittsburgh's steel industry, but the all-women welding crews that had built LSTs disappeared into history. James Washington returned to Alabama. Margaret Chen moved to California. Dorothy Martinez, missing 2 fingers, worked as a grocery clerk until retirement. None of them received medals. None testified before Congress. Their names appeared in no history books. The LSTs themselves fared better. Of the 1,051 LSTs built during World War II, over 900 survived the war. 26 were lost in combat, 13 more in accidents and rough seas. That survival rate, 85%, spoke to the quality of construction that Dravo's assembly line methods achieved. These weren't disposable vessels rushed into service. They were properly engineered, correctly welded, stress-relieved ships that performed under conditions that would have destroyed traditionally built vessels. The post-war Navy kept hundreds of LSTs in service. Korean War amphibious operations relied on LSTs built at Dravo and other Midwest yards. The Incheon landing in September 1950 used LSTs that were 8 years old, still functional, still beaching themselves on hostile shores. Vietnam saw LSTs performing supply missions into the 1960s. The last LST built during World War II, LST 1179, wasn't decommissioned until 2002, 60 years after construction. The legacy of Dravo's production innovations extended far beyond LSTs. The modular construction philosophy, prefabricated sections built in parallel and assembled rapidly, became standard practice in naval construction. The stress-relief welding sequences, center-outward patterns that distributed residual stress evenly, were codified into American Welding Society standards in 1947. Every welded ship built after the war incorporated techniques developed at Neville Island between 1942 and 1945. The civilian shipbuilding industry absorbed the lessons more slowly. Post-war commercial shipyards initially returned to traditional methods, skeptical that assembly line techniques would work without wartime urgency driving innovation. But by the 1960s, when container shipping demanded rapid construction of standardized vessels, the industry rediscovered what Dravo had proven. Modular construction, prefabrication, stress-relieved welding, all became standard practice because the economic advantages were undeniable. The transfer buggy system, Dravo's solution for moving massive hulls through progressive construction berths, influenced shipyard design worldwide. Modern shipyards in Korea, Japan, and China use variations of the same concept, moving ship sections through specialized construction stations rather than building everything in one location. The principle that hulls should move through the factory rather than factories moving around static hulls. That was Dravo's insight in 1934, proven at scale with LST production. But the story has uncomfortable truths that celebration obscures. The assembly line philosophy that made rapid LST production possible worked because it reduced complex shipbuilding to simple, repeatable tasks. Workers became specialists in single operations, efficient but narrow. When the war ended and those workers returned to civilian employment, their specialized skills were often worthless. A welder who could make perfect vertical hull seams on LSTs couldn't necessarily weld pipe or fabricate structural steel. The training that made them valuable during the war left them unprepared for post-war work. The human cost of three-shift continuous operation was significant and largely unacknowledged. Workers pushed beyond safe fatigue limits made mistakes. The injury rates on night shifts were double day shift rates. Dorothy Martinez wasn't the only worker who lost fingers. Others lost hands, suffered burns, died in industrial accidents that wartime production schedules minimized as necessary sacrifices. The official statistics listed 11 worker fatalities at Dravo's yards during LST production. The unofficial count, including deaths from long-term exposure to welding fumes and accidents unreported to maintain production schedules, was likely higher. The pressure to maintain production quotas meant quality inspections were sometimes rushed. The 8% reject rate sounds acceptable until you realize it meant roughly 1 in 12 LSTs had significant defects that inspectors caught. How many minor defects passed inspection because time pressure forced inspectors to focus only on critical failures? The Navy never published comprehensive failure analysis of LST structural problems, but operational reports mention hull cracks, weld failures, and ballast system malfunctions that required field repairs. The sailors who crewed LSTs paid the price for marginal quality. 26 LSTs sank in combat, but the loss circumstances varied. Some took direct torpedo hits that would have sunk any ship. Others broke apart in rough seas, suggesting structural weaknesses. Still others suffered catastrophic failures from single shell hits that shouldn't have been fatal. The assembly line production that put LSTs on beaches also put sailors in vessels that were good enough to launch, but not perfect enough to guarantee survival. Yet, the alternative was worse. Without Dravo's assembly line innovations, the Allies would have had perhaps 200 LSTs by D-Day instead of over 1,000. The invasion of Europe would have been delayed, possibly into 1945. The Pacific Island campaigns would have stalled without adequate amphibious lift. The strategic calculus was brutal but clear. Better to have 1,000 LSTs with an 8% defect rate than 200 perfect ships that arrived too late. Winston Churchill's assessment proved accurate. The destinies of two great empires were tied up in these goddamned things called LSTs. And those LSTs existed in decisive numbers because a Pittsburgh barge company figured out how to mass-produce ships using techniques borrowed from automobile manufacturing. The innovation wasn't in ship design. It was in production methodology, in recognizing that complex things become buildable when you break them into simple, repeatable operations. The irony is that the people who made it happen remained virtually unknown. James D. Berg and Vincent B. Edwards, the Dravo executives who committed to the impossible production schedule, returned to bridge construction and barge manufacturing after the war, without public recognition. Carl Rasmussen, the welding supervisor who managed the hot ship program, never received the Navy's Civilian Service Award. The 16,000 workers who built 145 LSTs in 3 years, scattered across America. Their contributions forgotten. Dravo Corporation continued building river vessels until the 1980s, then diversified into steel fabrication and mining equipment before finally being absorbed by other companies in the 1990s. The Neville Island yards closed in 1982. Today, a small historical marker stands in a quiet park where the East Yard once operated. Nothing remains of the berths, the fabrication shops, the transfer buggy rails, the welding bays where 16,000 people proved that industrial capacity, properly organized, could change the course of history. 3 LSTs still exist as museums. LST 325, berthed in Evansville, Indiana, is the only operational LST in American waters and offers tours. LST 393 in Muskegon, Michigan, serves as a floating memorial. LST 510, converted to a ferry called the Cape Henlopen, still carries passengers across Long Island Sound, a working reminder that the ships built for war proved durable enough for decades of civilian service. The final assessment requires acknowledging complexity. Dravo's assembly line production won the war. The 1,051 LSTs, built faster than anyone thought possible, delivered Allied armies onto hostile beaches from North Africa to Okinawa. The production innovation was genuine, transformative, and permanently changed how ships were built. But that same production system prioritized speed over perfection, quantity over individual worker well-being, and strategic necessity over long-term consequences. The Danish immigrant who promised impossible tank production, the Pittsburgh company that proved ships could be mass-produced, the 16,000 workers who welded a fleet into existence, they all succeeded by accepting trade-offs that peacetime would never tolerate. That's the uncomfortable truth of industrial warfare. Victory goes not to those who build the best weapons, but to those who build adequate weapons fastest. Dravo understood that truth and executed it flawlessly. The LSTs didn't need to be perfect. They needed to exist in overwhelming numbers, needed to arrive in time, needed to function long enough to matter. By that standard, Dravo's achievement was absolute. Every LST that beached at Normandy, every tank that drove off Pittsburgh-built ramps onto French sand, every soldier who reached shore because an LST delivered him there, all of them owed their presence to production methods developed by people whose names history forgot. That might be the most important lesson. The engineers, welders, supervisors, and workers who built the machines that won the war rarely received credit for the victory. They returned to obscurity while history celebrated generals and admirals. But wars are won in factories before soldiers fire the first shot. Dravo proved that in the most decisive way possible. They built victory, one welded seam at a time, using techniques that looked like magic but were actually just brilliant industrial engineering executed by ordinary people doing extraordinary work. Thank you for reading. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.